So today's topic would be nomenclature. Okay? Nomenclature of organic compounds. Write it down. Today's topic would be nomenclature of organic compounds. Okay? Now, what do you mean by the nomenclature of organic compounds? Just understand. When I talk about the nomenclature of organic compounds, right? It means this. Yes. When I talk about the nomenclature of organic compounds, okay, it would mean what? It would mean that you have to name. There was an organization I used which is called IUPAC. IUPAC is called as International Union of Pure and Applied Chemistry. Okay? International Union of Pure and Applied Chemistry. You understand? So when basically we are talking about the IUPAC, so IUPAC has given certain rules to do what? Because there are lots and lots of carbon compounds. There is no end to the number of carbon compounds. For now, we know that 600 carbon atoms can join to form long chains. And when such 600 carbon atoms can join to form such long chains, what would that mean? It would mean that so many compounds could be formed where carbon could be joining in the straight chain or in the branch chain and so on. But I hope you're understanding that we have to name the compound so that these names are universally accepted. It's not that you can name a compound by certain name in India and the name for that compound would be different in UK and that name would be different in Dubai, etc. It's not like that. A compound has to have a universal name, and to keep that universal name, IUPAC has given certain rules. So those rules we would be doing. Okay. Very basic method of naming the compound would be rule number one, you have to decide the word root. You have to decide the word root. Okay. Now, what is word root? Word root is decided by the number of carbon atoms. Word root is decided by the number of carbon atoms in the compound. You understand? Like, for example, if there is only one carbon, so number of carbons, and here is the word root. Here is the word root. Now, how does it work? If there is one carbon in the compound, the word root shall be met. If there are two carbons, three carbons, four carbons, five carbons, six carbons, seven carbons, eight carbons, nine carbons, 10 carbons. So on that basis, if there are two carbons, the word root would be eth. If there are three carbons, the word root would be prop. If there are four carbons, the word root shall be but. If there are five carbons, the word root shall be pent. If there are six carbons, the word root shall be hex. If there are seven carbons, the word root shall be hept. If there are eight carbons, the word root shall be oct. If there are nine carbons, the word root shall be non. And if there are 10 carbons, the word root shall be dec. Similarly, if there are 11 carbons, the word root shall be undec. And if there are 12 carbons, the word root shall be dodec. I can tell you word root still 100 carbons, but that's not required. What is required is that up till 12 at max, you will be getting the compounds. So you should be able to know the word root. Understood? Right? Right? Okay. Next, what do we have in here? Take the screenshot. Next, what do we have in here? We have the other part of it. The other part of it would be the suffix. Now, depending upon what is present. So if there is all in the entire chain, you see there is all single bond. All carbon to carbon single bond. All carbon to carbon single bond. So the compound would be, and by nature, the compound would be an alkane. So the suffix that you will be using at the end of the name would be ane. Suppose in the entire chain, at least at one place, you find a double bond. Okay, at least in anywhere between any carbons, like these are the two carbons you're finding double bond. This double bond could have been here also. This double bond could have been here also, isn't it? This double bond could have been here also. There is a possibility that this double bond in this long chain could be here also. So double bond could be this place, can be at this place, can be at this place. It could be anywhere. Are you understanding? So in the entire carbon chain, wherever you find a double bond, maybe one, two, minimum one carbon, two carbon double bond, then by nature that compound becomes an alkene and the suffix becomes an ene. Do you understand? That suffix becomes an ene. Similarly, we have carbon to carbon chain, but at least at one particular carbon carbon bond, there must be a double bond. There must be a triple bond like this. It could be at any position. It could be like this long chain, and the triple bond could be here between these two carbons. Do you understand? That the triple bond could be somewhere here. Here. It could be between here. Do you understand? So the point is that you have this triple bond anywhere in the chain. And when you have this triple bond anywhere in the chain, it would mean what? It by nature would be an alkyne. And the suffix would be ine. Are you understanding my point? Right? And when this is alkyne, what would that mean? Just tell me. When this is alkyne, what would that mean? It would simply mean that the suffix that you're going to use would be an ine. So for alkanes, the suffix, that means the name that you use at the end, would be ane. If you see a double bond, you identify that this compound would be by nature an alkene. Alkenes has a common name called as olefins. By nature, they're also called as oils. All the oils, all the olefins by nature are oils. And all alkanes by nature are paraffins. The paraffin wax that you know, so the shoe wax, the shoe polish, or the Vaseline, all of these, all of these. Do you understand my point? Do you understand, right? Similarly, if in the compound you get to see the structure OH, there could be a long carbon chain behind. That doesn't matter. There could be a long carbon chain anywhere in the group you see OH. Anywhere. No matter where you want to see OH. If you see OH, understand the suffix would be ol. This compound by nature will act like an alcohol. This compound will show the properties of an alcohol. Whether it is an edible alcohol or not, that is a different thing. But this compound will show me the properties of an alcohol. Are you understanding my point? Okay, right. Next would be a long carbon chain could be there. And in this long carbon chain, in the end, we get to see this C double bond OH group. Sometimes you also write it down. This could be a long chain. This could be an aldehydic chain. This could be an aldehydic chain. So in the end, you write it down either as C double bond OH or you write it down as CHO. Okay, you either write it down as C double bond ONH or you write it down as CHO. It is aldehydic chain. So the name, the suffix of this compounds shall end with al, al. And understand that aldehydic group is always a terminal group. Okay, it is always a terminal group. You understand my point? It is always a terminal group. Terminal group would mean this is C double bond OH. It will always come at the corner, either this carbon or this carbon. No other place it could come. That's the functional group. So terminal group means that it is a functional group which comes at the last carbon. So you will have this carbon chain. You can have either CHO at this carbon or you can have the last carbon here also. You understand my point? So by nature, if you get to see CHO group, it is an aldehyde by nature and the suffix shall be al. Similarly, if I have a long carbon chain and at one terminal carbon I get to see C double bond OH. That means 1, 2, 3 COOH. We write it down primarily as COOH, but you understand that these two oxygens are not connected to each other. Do you understand? So if, for example, these two oxygens would have been connected to each other, that would mean that it would be, I would have written it down as CO2H. When do I write down CO2H? That would mean that, when both the oxygens are connected to each other. But in this structure, it is not so. The oxygens are not connected to each other. I hope you're understanding. These two oxygens are sort of not connected to each other. These two oxygens are connected to carbon indirectly. So one oxygen is connected to carbon with a single bond, and one oxygen is connected to the carbon with a double bond. So this would be 1, 2, 3, 4, and that's the structure. So we get to see either this C double bond OOH, or we compress it down to COOH like this. No matter how you write it down, the functional group by nature is a carboxylic acid. Now, where do you get to see the carboxylic acids in real life? Alcohols is easy to understand. All sanitizers, all drinking alcohol. You understand? All of these are alcohols. You understand? And similarly, this could be this. So COOH. Either this terminal carbon. I hope you're understanding what is a terminal carbon. The cornermost carbon atom. The cornermost carbon atom, not the middle ones. So you write it down as COOH like this also, like this also, or like this also. Whichever way you want to write it down. Whichever way you want to write it down. Yes or no? Right? So by this, now where do you find all the carboxylic acids? All the carboxylic acids are of the form, no matter you have kiwi. Kiwi is a fruit, you must be knowing. Oranges, right? Tea, vinegar, apple, all the fruits, they have certain acids in them. Those acids are edible. We can eat those acids. And all these acids which we are able to eat or consume are all carboxylic acids in nature. I'm not saying all carboxylic acids are consumable, but yeah, you find most of the carboxylic acids in fruits. Like apple has malic acid. Apple has malic acid. Tea has tannic acid. Right? Tamarind would be imli. Tamarind has tartaric acid. Milk has lactic acid. Are you understanding? So all these acids we have with us. All these acids are edible. All these acids are consumable. And by nature, all of these are carboxylic acids. But also understand there is an acid called as formic acid, also known as by another name which is called as methanoic acid. This acid is actually present in the ant sting. This acid is present in the ant sting. What is ant sting? Like when ant injects the poison in the body, by nature the poison is methanoic acid. So some carboxylic acids are harmful also, but most of them are useful. The most commonly used is vinegar. Vinegar is widely used. Widely used. Do you understand my point? So this is carboxylic acid, right? So this consists of ethanoic acid, and it is also called as acetic acid. Do you understand my point? So my point here is that when we are doing this particular terminal carbon atoms, you will find all these acids will have this group. COOH, this group is bound to be found in these compounds. There is no second thought. If I talk about any carboxylic acid, understand that it will always have COOH group in it. Always. No matter what. Do you understand the point? Hmm? Now understand. Similarly, now if I have C double bond long carbon chain, and the functional group here would be what? The functional group here would be oic. So suffix here would be what? Oic. Oic. You see here oic acid. That would be the suffix. Like for example, if you see here, you see oic acid, ethanoic acid, methanoic acid, oic word would be there. So by the ending oic, you understand that it consists of COOH group. Similarly, what do we have in here? There could be a long carbon chain. And when we have this long carbon chain, we have C double bond O. Only that's it. It's a middle group. Okay, it is not found at the terminal carbons. It is found at one of the central carbons. It is found at one of the central carbons and not at the terminal carbons, and not at terminal carbons. Do you understand? So you just have C double bond group, and on the either side of it, you have a long carbon chain. So two carbon chains, one on the right side, the red carbon chain, and the blue carbon chain, one on the left side. The blue and the red carbon chains could be either of the same number of carbon atoms, or they could have different number of carbon atoms. So both the chains, both the carbon chains on either side of on either side of C double bond O could be could be of the same size. When I mean the size, it would mean what? It would mean same carbons or different number of carbons or different sizes or different sizes. Do you understand? So that's the thing. So this carbon chains, these carbon chains, we call them as R. We mark them as R. These carbon chains are also called as alkyl groups. So I could say that this is R and this could be R dash. These R and R dash are two different carbon chains which could be same or different. So I would say R or R dash. So I would write it down like this: R C O R dash. So R basically means a long carbon chain. A long carbon chain. Do you understand my point? It would mean a long carbon chain. Okay? Then what do we have in here? So there are other groups also. Like for example, in the carbon chain, we could have Cl. So these are the certain substances that we use always as prefixes. Certain compounds or certain groups we always use as prefixes. Like for example, we use as prefixes. Like for example, we have NO2. So if you see NO2 group somewhere, you will always use that nitro, and that will always be used before the word root. Prefixes are always used before word root. Before word root. Do you understand? Like for example, if you see Cl, you will always say chloro. If you see Br, you will always say bromo. If you see I, it will always be iodo. If you see F, it will always be fluoro. Do you understand, Ayush? So we have nitro, chloro, bromo, iodo, fluoro, like that. Understood? So these are certain substances and thereby all alkyl groups. Like for example, if I see CH3 group, I shall always name it as methyl. And there could be lots and lots of alkyl groups. Right? So these are certain compounds or certain groups that you will always see as prefixes. And write down one statement that all alkyl groups are. Now, what is an alkyl group? I'll just explain it to you. All alkyl groups are prefixes. All alkyl groups are prefixes and are always side chains. And are always side chains. And are always side chains. All alkyl groups are prefixes and are always side chains. Understood or not? Right? That's the important part. Understood. So that's how we sort of work with these. Do you understand? Right? Now just see. Now just see. So when we have to name a compound, now what is the rule? Number one. So the order of the name shall always be always decide the word root first. Then you decide the primary suffix. Then you decide the primary suffix. Okay. The primary suffix shall be "-ane", "-ene" or "-ine", depending upon what kind of bonds we get to see between the carbons. En you choose when you get to see a double bond at least at one of the positions, and ine you get to see if you see a triple bond. And then finally, followed by that, a secondary suffix. So secondary suffix, under the category of secondary suffix, we have a, ol, al, oic, and on, ketone. For all the ketones, what is a ketone? RCOR dash. That is a ketone. All carboxylic acids, all aldehydes, and all alcohols. We have the secondary suffix. And before the word root, we place in the prefix. The prefixes have to be placed in the alphabetical order. In the alphabetical order. Okay, so the prefixes are to be placed in the alphabetical order. So prefix plus word root plus primary suffix plus secondary suffix and so on. This shall form your name by the IUPAC rules. Do you understand? Write it down. Now, how does it sort of work? Just understand. There is also one more term which is called as an alkyl group. Now, how would you name the alkyl group? Like, for example, understand. Just tell me what is this compound? If I say C, 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 and I complete all the valencies of carbon by hydrogen. So we have H, 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 isn't it? So what do we have in here? How many carbons do you think we have? 1, 2, 3, 4. 1, 2, 3, 4. We have 4 carbons here. Just have a look at the word root. What is the word root for 4 carbons? Bute. Do you understand? What is the word root for 4 carbons? Bute. Yes or no? So what do we write it down? We write down the word root first, bute. Then what do we get to see? Single bond, single bond, single bond. All the places between the 2 carbons, we have a single bond. So we write it down butane. You understand? We write down butane. Because ane stands for alkene. Are you understanding? Ane stands for alkene. Understood? Right? That's how the name would be. So for example, if I give you this compound, so if I give you this compound, I complete all the valencies with hydrogen. So hydrogen, see, understand, this structure that I've drawn for you here, this structure is an open chain structure. This structure is an open chain structure. Do you understand? Open chain structure. What do you mean by an open chain structure? Where all the bonds are openly shown. The carbon-carbon single bond, the carbon and hydrogen bonds. Do you understand? All the bonds are openly shown, forms an open chain structure. Do you understand? So I could have written down the structure in a very compressed format also. I could have said that okay, there is a single bond. I would show the carbon-carbon bonds and I would just compress down all the hydrogens along with each carbon. So if you have 3 carbons connected to this carbon, yes or no? I will just write down these 3 carbons H3, CH3. I have 2 hydrogens connected here with this carbon. I would write it down CH2. If I have this hydrogen, so I would write it down CH2. And if I have this carbon, I would write it down CH3. Are you understanding? So this would be my condensed formula, condensed structure. So in either way, they would write it down. All I am concerned with the carbon-carbon bond, nothing else. Because I know that no matter what, hydrogen cannot form more than a single bond. Hydrogen shall always form a single bond. So that's not the point of concern. The point of concern shall be the carbon-carbon bond. And if that is a single bond, definitely that compound is an alkane by nature. And the suffix would be ane. Understood or not? So now if it makes sense to you, if can I write it down like this? CH3, CH2, CH, CH2, CH2, CH3. Are you understanding? So it would be 1, 2, 3, 4, 5, 6. It would be hex, 6 carbons. First, always count so rule number 1, always count the longest chain. Always count the longest chain. Yes or no? Do you understand? When you count the longest chain, what would that mean? You have 6 carbons in it and then you decide the word root. So 6 carbons the word root shall be. 6 carbons, the word shall be hex. Okay, good enough. Hex and then single bond between two carbons. Nowhere you get to see a double bond. It is an alkane, hence the name hexane. Because for alkanes, the suffix that we use is ane. That's the name. But do you see, you have just named this part of it. Now still Cl is left to name. And Cl, I told you that it is by nature will always be a prefix, isn't it? That will shall always be a prefix. So it would be 1, 2, 3, 4, 5, and 6. And it shall be chloro. Yes or no? So where do you get to see this particular part? Just tell me. It would be what? It would be 1, 2, 3, 4. You have to now number the chain, understand? You could number the chain from left to right like this. You could number the chain from here to here. Or you could have numbered the chain like 1, 2, 3, 4, 5, 6, isn't it? From here to here also you can number the chain. From left to right or from right to left. Yes or no? Now, which numbering do you think would be better? So understand. So from if I take the red numbering, do you see 1, 2, 3, 4, 5, 6 works? Because according to this numbering, 3 has chloro in it. So chloro is actually connected at the third carbon. That's what this number is showing, isn't it? If the Cl is there, chlorine is connected to the third carbon. If I look at from right to left, you see that chlorine, according to the blue numbering, chlorine is connected to the fourth carbon. We have to see that particular numbering where the carbon number is smaller, where the carbon number is smaller. Do you understand? So we do not prefer the blue numbering. We always prefer the red numbering. Do you understand my point? So it shall be 3-chloro, 3-chlorohexane. This is called as a lowest locant rule. This is called as a lowest locant rule. Are you understanding? What is the lowest locant rule? A lowest locant rule would mean that you have to choose that particular carbon on which chlorine is connected, on which the side chains number should be the least possible number that can have been, that we could have. So chlorine, basically, if I number from 1, 2, 3, 4, then according to the bottom numbering, it could have taken fourth number as well. But I don't want to give it a fourth number because I know that if I take the red numbering in preference, the red numbering shows me that chlorine is connected to the third carbon. And I always have to choose a smallest number to decide, the side chain is connected to which number carbon in the main chain. So this carbon chain would be called as a main chain. I hope you're understanding. Yes or no? Right? So that's the structure. So the name of this compound shall be 3-chlorohexane. 3-chlorohexane. Understood or not? Right? Okay. Now if I name this compound, understand? So if I have this compound, carbon, 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 and we have this, and I have this, and I have this. So, and you are supposed to name this compound. So understand what am I doing? Do you understand that carbon is this carbon? This carbon is forming one single bond here with this carbon, one single bond here, and one single bond with chloro. So how many hydrogens do you think I need to attach to this carbon? Only one. I need to attach two hydrogens here because it is already connected with itself. 1 and 2 and 3 and 4. Are you understanding? And we have this. And we have this. So this is forming 1, 2, 3. Do you understand? So fourth carbon would be the valency would be completed by H. And here the two valencies shall be completed by H. Are you understanding my point? Yes or no? So what do we have in here? So we do not have to write down the expanded structure, the open chain structure, but just to explain it to you that how am I putting up these H's. So I'm just compressing them down, all the H's together so as to just understand how the naming has to be done. So it shall be CH2, it shall be CH, it shall be CH, it shall be CH2, and it shall be CH. Understood or not? So what do we have in here? We have this. So we have 1, 2, 3, 4, 5, 6. How many carbons? 6. Just have a look at the word root. Always decide the word root first. So for me, it shall be hex. It shall be hex. Because 6 carbons are there. Number of carbons are 6. Number of carbons are 6. So word root shall be hex. Understood? Then what do we have in here? Then what do we have in here? We have 6 carbons. Then we get to see that everywhere there is a single carbon to carbon, single bond, carbon to carbon, single bond, and a double bond. Even if at one particular place I'm going to see a double bond, it means by nature it is an alkene. And if by nature it is an alkene, so the word root shall be hexene. So I have decided the word root. Just have a look the scheme. How does it work? The scheme is word root plus the primary suffix. Yes or no? So primary suffix either would be "ane", "ene" or "ine". So it is going to be "ene" in this example because you are getting to see a double bond. So you have completed naming the carbon chain. Are you understanding? Then you are still left to name bromo and chloro. Now, for bromo, the B comes first alphabetically, and for chloro, C comes later on. So first I'm going to write down bromo alphabetically first, and then I'm going to write down chloro. So there is a bromo and there is a chloro. Understood or not? What do we have in here? Bromo and a chloro. When we talk of bromo, I hope you are understanding. For bromo, just see what is happening. There is this third carbon, isn't it? So I would say 3 bromo and chloro is connected to 5. It shall be 5 chloro. So the name of this compound shall be 3 bromo, 5 chloro, hexene. Understood or not? Right? But the point is that you have to understand one more thing here, that you could have numbered this chain like I have numbered it according to this 1, 2, 3, and 4. I could have also numbered this chain like this also. Right? 1, 2, 3, 4, 5. I could have numbered this chain like this also. But why I haven't numbered this chain like this? But why I haven't numbered this chain like this? Because always, write down one thing, always give preference to double bond. Always give preference to double bond. When I say preference, you understand the compound shall be showing the properties of the double bond. Are you understanding? This compound shall always show the properties of the double bond. So single bonds, no matter how many single bonds are there in the structure, this compound shall always show the properties of the double bond. Do you understand my point? Yes or no? Right? So when I say the preference, it would mean that which particular portion of the compound is dominating in its properties, which particular part of the compound is showing its properties. That's what you understand by preference. And whosoever's property is being dominant, that gets the smallest number. It's like this, like, when you come first in the class, the value is more, but the number is small. Are you understanding? Right? So you give a lesser position to that, the number is 1, but its value is more. So that's the point. So first, second, third, fourth, fifth, sixth. That's the red numbering would be more preferable because double bond comes here. So it would be like this. So I would not consider this particular part here. Yes or no? Smallest number. So you say, double bond comes first in the class. So double bond gets the first position. Yes or no? Right? Then what do we have in next? What do we have in next? Just have a look. If I draw the structure for you. If I have this structure for you. And this is a structure. So why am I connecting? Because this carbon is already formed 1, 2, 3, 4 bonds. So I will not be connecting any hydrogen to this carbon. But to this carbon, I shall be connecting 1, 2, and 3. So 1 hydrogen and I'll be connecting 3 to this. How many carbons do I have in this structure? 1, 2, 3, 4, 5. So 5 carbons, the word root shall be pent. And there is a double bond at the second carbon. It starts at the second carbon and ends at the third carbon. When I look at the chain, the double bond starts at the second carbon and ends at the third carbon. Are you understanding? So I would say it would be pent 2-ene. You also have to tell me the position also of the suffix also sometimes. It was pent 1, it was hex 1-ene. I do not write down 1. But here it would be pent and ene. Pent is the word root because for 5 carbons. Ene because of the double bond. But ene is coming at second carbon. It would be pent 2-ene, right, Ayush? Pent for 5 carbons, ene for double bond, and ene is coming at what position? At second position. Because the double bond starts from here. So if I draw this, it starts on second carbon and it ends at the third carbon. Do you understand? So it shall be pent 2-ene. And where is this NO2 group? Where is this NO2 group? NO2 group would be my side chain and that would be prefix. So it shall be 3 nitro pent 2-ene. That's the name. Do you understand? That's how you're supposed to name the compounds. Understood? So similarly, if for example, you can reconnect back.